This conference will now be recorded.
Okay, good morning, everybody. Today we're gonna cover a bunch of the thermal stuff. So over the last couple of weeks, I've put a bit of time into the thermal design. And so there's a couple of areas. Again, it's very cartoony, so please excuse my crude thermal and mechanical abilities. Hence why I think we're going to need some expertise on this going forward if people can help. And it does include the interconnect as well. So in terms of some thermal interconnect, actually. So that's the main topic I've got for today. I don't think we'll have time for anything else. Let's just get going. I don't believe we have anybody new on the call right now. So we don't need to do any introductions. So let's get into it. So I'm going to work basically from the model. I haven't prepared any slides. So let me just bring up the model. And let me just shrink this down a little bit for me. Oh, didn't expect that to happen. Good morning. Who just joined?
Hey, Alan. It's Roger.
Hey, Roger.
Hi.
Join in. Let me just pop you in. Okay. So as we discussed, I believe briefly on the last call, we were talking about the actual thickness of the E3 modules and actually not having much of a height profile. I did put some slides together on that, but long story short, I've decided that probably the normal width of the E3 module is 7.5 millimeters for a 1T thickness, compared to 16 millimeters for the 2T. I did do some investigations, and one of the controller companies that will remain nameless at the moment, but they kindly gave me their mechanical spec of their controller chip for CXL.mem, and they do comply to the single width thickness with their chip size, which is good. But I do know that FPGAs that I know Samsung use in their smart SSDs and smart memories do exceed it, at least with the lids on. It's whether they would remove the lid, but that would be a special requirement. So anyway, I decided to make the module width 8.5 millimeters, and where you would put this copper lid on. So even if it was a 7.5 millimeter module, then this 8.5 millimeter gives you a little bit more flexibility. So that's what I plan on running with, so that we don't have to go and consume 2 slots. But I've also squeezed it in to the existing module format, including my cooling ideas. However, I believe that we probably need to expand the width of the module by about a millimeter per one of these modules, so about 8 millimeters, maybe 8 to 10 millimeters, to take it up from 102 to 110 to 12, to actually get this to work. And this is, but before I get carried away, I really wanted mechanical input on, does this really make sense? And I also need thermal simulation on will this actually cool these modules? So so that's basically it. Let me just
Can I make an observation, Alan?
Yeah. Yes.
Presumably, with that design, there's nothing stopping you going to a double thickness module, so long as you avoid the connector. It's just as we've seen with PCI.
So that is the case, Greg. Yeah, that is the case, Greg. But the idea here as well is we're finding like a number of CXL .mem modules are actually double thickness from Micron and Samsung. And that's, I believe, because they are going over the 25-watt power budget, or they may well be. And the double thickness is 40 watts. The hope I've got here is that we can actually cool 40 watts with a single width. So this is all about density, really. So and I did it at Memcon. I got Micron to take the lid off of their air cooled with air fins on it, and see that it was a single width thickness with, you know, so it looks like it's possible to easily convert these double width ones to single width. I mean, that'd be ideally where we go. And I was thinking that maybe normalizing to just the E3.S for everything, because we are conductively cooled rather than air cooled, might keep us in this much denser configuration. The problem with going to double width modules is you lose 50% of the modules, obviously, in terms of what you can pack in. So, but yeah, good question. There are some features in this design that would need to be addressed to support the double width modules. But yes, technically speaking, you can. So good point.
And when you say conductively cooled, I take you really mean heat pipe.
Yeah, so no, actually, so this is like a cold plate on the lid in the floor of the module itself that will contact all the significant components and conduct the heat down to where the water is flowing through on this here. So that's where I'm just going to get into the detail now.
I would say in the specification it would make sense to allow for heat wicking, so heat pipe type design, because it does provide a lot more thermal transfer.
Sure, absolutely. Yeah, if you could fit the heat pipe, yeah, the closed heat pipes in your lid, hey, happy days, even better. And maybe we do have to go there. I'm hoping we don't have to go there for 25 watts or.
Well, the reason I say this is because I've been having a look at the design of microfluidic heat pipes for this, and you can make them very thin, and you can basically route two pieces of copper.
Yes.
With the pipe, with essentially, you know, the pipe work in it.
Right.
And then you join them together, permanently seal them, and then you can take advantage of having a liquid in there, acting as a heat wick, but with all the benefits of it being a solid component, no liquid joints.
Yeah, so that's that's where the thermal simulation, I think, will come into play, is to whether something like that is needed on top of this or is better. So without getting too much in the weeds of that now, let me just unpopulate these EDSFF modules for a moment. Oh well, yeah. So maybe just one thing to double say here is let me just. So the idea would be here, if I just peel the lid off this one, you would pick up, so your big power hungry, I'm assuming about 15 of the 25 watts would be in the controller, for example, in the media device, and maybe 10 would be spread around all of the other media itself, as an example. And so this would be the critical thermal interface here, which is close to where the water is flowing. And these would be gap padded to the top and bottom of the case to conduct things through to down. So that's the idea, and that's exactly how Micron and Samsung do it right now. So that's
Alan, how thick do you have those copper plates right now?
This is 1 millimeter is the plan.
Okay. Yeah, I think you'd want to look at mechanical simulations as well, just with a lot of gap pad surface area like that.
Right.
You're looking at a risk of warping or bending that cold plate.
Oh, the lids. You might need more mounting holes on the. Fair enough. I see what you mean. Yeah, because
the plate.
Yeah, no, fair point. Okay, so actually, I could do is taking some notes on this. So gap pads bending the lid.
There are some different ways to get around it. Like there's some like zero force gap filler, things like that. But
yeah, actually, just on that, now you're mentioning it, let me just get rid of the body. It's actually thicker than 1 millimeter. The lid itself is 1 millimeter, but it does sink into the it sort of sinks in. So it's actually more like 2. So it may not be overly bendable with the frame around it, but yeah, I take your point. So yeah, this is where I need the mechanical expertise.
Yeah.
Okay, all right. So just depopulating these. Now this gets into how. So I was talking about wedge locks before, and if you remember, the module was full height of the E3.S modules, of the EDSFF modules. But let me just get rid of these sketches. Okay, so what I've done here, you'll see that zooming in, I've actually brought a bar of copper across in front of each of these slots. And this copper is extremely thin at the moment. And that's why I'm saying we're going to need to add at least 1 millimeter. This copper thickness is 0.6 of a millimeter in terms of making it all fit together with the 8.5 millimeters. And then I've allowed, this is where Samtec can maybe help. I've got this like standard like electrical contact connector that I'm assuming would somehow be welded or somehow connected to the, thermally connected to the copper here, and this would be where you'd get the mechanical interference with the copper plate on the module for the heat transfer. And similarly on the sides, we'd have a similar connection. So as you slid the module down, you would get this interference fit for the thermal conduction. Now I'm not sure how bad that's going to be for the thermal interface. So that's something we could literally take one of these modules with one of these sections in isolation and then do some thermal modeling on that to see if we could cool 25 watts with the wattage being distributed across the module's height, obviously, as I just said. So the way this works, and the other thing to look here is I've now brought the water down into this base module into the underneath frames. The water comes in here, and it comes in obviously on the other side here. The blue ones are the cold water in. So we're bringing the water in, and the way I've envisioned this, I haven't built the pipes inside this brick yet, but the water would come in, would effectively go up and down. So the water would be running close to these pillars, and then it would shoot along underneath here. This copper thickness at this point is about no, that's not the right one. Is about 3 millimeters thick. There you can see down there, it's about 3 millimeters. And that would get thicker if we made the module slightly wider. And so there would be water channels running down all of these in between every single module. Then when it hits here, it would come up through this wall and then back down through the wall on the other side and carry on along. And so the way I envisioned it is the cold water would come in on one side. It would probably go down the outer edges and the outer couple of modules this way. It would then return back down in the other direction, back to the middle here. And then I've not shown this bottom one, it would actually, the water would transfer through to the top of the module and then go across the 1 kilowatt processor and then eject out of these out of the external ones. So that's the flow. So there would be water, connecting to all of these connector areas, and so that's the idea. So any questions.
Just a couple of thoughts. So I guess inside those raised areas, you could potentially do phase change, because clearly we're not going to use water. It's going to be something like Novac with a low boiling point. So that height would potentially allow you to use those as reservoirs for phase change to occur. The other thought I had is, are we going to need to think about EMF modelling as well, given we've got metals are obviously good for grabbing EM emissions, but given how tight they are, do we run the risk of them propagating EM fields between the modules?
Well, the modules will be sealed units, right? So, they're in their own little metal case already, right? So I'm assuming EM is not going to be too big an issue.
Yeah, if you're already capturing it there, you're right. Yeah.
But yeah, in terms of like the chips that are on the board down here, especially if modules aren't plugged in, I'm not sure if there's any radiation issues. So radiation has, when I was working with IBM, they did bring this out. But you could potentially put some lid over the whole lot of this, or some door over the lot, which could be EMC. So the EMC side of things is a good question. I'm relatively happy about the EM side of things personally, just in my gut feel of it, but but gut feel is not necessarily good enough. But I think that's a second order concern in my mind right now compared to this. So it's a mechanical and thermal designer. Clearly, if I'm a bit reticent to just go straight into the design of the FPGA module itself until we say, well, we think we've got a module that that's mechanically the right size and can be thermally cooled based on what we're trying to do. So that's really why I'm focusing on this area here right now. Now, the other thing to bear in mind here, by the way, chaps, is that you'll see here. In fact, I think I've got too many connectors turned on here. I've got the Samtec and the I've got the Samtec connectors ones turned on and the MCIO ones. So let me just turn off the Samtec cables a moment. There we go. So this is the MCIO connector being shown here, and you'll see here that this actual cable connector also has a little bit of copper. So I've sort of extended the casing. So you've got, and in fact, we can. It doesn't need to be this high. I think the copper is 3 millimeters above where the paddle card is. So we can have an active little paddle card in here with near packaged optics or retimers for active cables, active copper cables. And again, that mates in a similar fashion with this connector from a thermal conduction to cool down active modules. So this is where, from Samtec's perspective, I'm hoping that you would consider doing Firefly, PCIe Firefly, in the MCIO format like this, and we could conductively cool it, as well as maybe putting fins on it like you do on the Firefly. So this is especially as this is going to become more important, I think. This is where I need a signal integrity analysis, and the presentation I did at the ODSA a couple of weeks ago, or the beginning of last month, or beginning of this month, was where I actually covered analyzing the losses in a channel and how you could maybe rebuild the channel much more effectively and be much more either lower energy or go further distances over copper before having to go optical. So there's a cooling of these as well if necessary. If not necessary, you just put a normal connector in and it doesn't mate to the cooling channel. So that's the sort of cartoon idea. Any other questions or observations before? Is it completely crazy? Does it seem somewhat viable, needing much more analysis?
I think it's a neat idea, Alan. I think for sure the biggest thing from the mechanical side would just be looking at all your tolerance stackups from you contacting a lot of different surfaces in different dimensions, and just making sure that would all work. Like you'd want to you need to eat up tolerances in different directions maybe from thicker gap pads that eat up those tolerances, or by other means. Because the moment you have a large, probably brazed structure like this, with multiple datums that you need to be contacting things with, that's where you start to have some tolerance stack up issues.
Yeah, so actually, so you bring up a good thing there on the tolerances, very good point. And the other thing here actually is, how do we make this beast? This is quite a complicated beast. And this is, again, where I'm the mechanical guy. So you can 3D print copper now. So I was thinking of 3D printing, but that's probably going to be exceptionally expensive from a volume perspective. So I don't know if you could build a mold for this in some form or fashion. So there was that side of it of can this be cost effectively manufactured is clearly.
I would have thought, looking at it, Alan, it's a 4-axis CNC job, made in 2 parts, and they're sandwiched together, and then you can get all your internal channels. But yeah, I mean there's manufacturing folks who are good at that. I mean, our aerospace folks will soon chomp through that type of problem.
Yeah. So I mean, on the one front, I quite like the. So by the way, that was the other thing is I'm trying to get this. This is a water channel design, which, you know, would be the same for everybody. This is the idea. This would be a step and repeat, and a recoverable thing as well. You know, if you need for. I'm trying to think of the energy. You know, energy-centric computing first, and so the embodied carbon. This modularity is all about. This is all reusable. You could actually, you know, when a processor chip or accelerator chip went obsolete, or you wanted to upgrade it, you could literally put all these things back in. You know, disassemble the module and reassemble it with the new processor or whatever. And so therefore you're reusing all the embodied carbon. So
I mean, the thing I like about it, just 2 pennies worth, is I'm spending a lot of time looking at VPX platforms at the moment, as you probably know, and yeah, it feels like something out of the Ark by comparison. And
yeah,
I think
the VPX. I mean, I did have wedge locks in the original design, which is inspired from the Vita world, right? The VME back in the day. And so, but I've moved. I said, do we need wedge locks, or can we do something with these type of sprung-loaded interconnect to get a thermal interface or not? That's the interesting piece on this. Oh, by the way, hi Suresh. Thanks for joining.
Hello.
Just check. A few other people have jumped in, so I just want to make sure I got everybody. Andrea M. Hello, Andrea. Is this your first time, Andrea? I don't believe I've got you in here. I can't hear you. Looks like your microphone might not be working. Okay. Well, welcome, Andrea. If you manage to get your microphone working, you could maybe briefly introduce yourself. Okay. I'll just make a note as well. Okay. All right. No. So, all right. So nobody's completely thrown me out the wall, but I think the thermal simulation will, and the mechanical analysis will be the guide of this. So I guess on mechanically, I've already convinced myself to extend this by at least another millimeter gap between each of these, meaning that these walls here would go from about 0.6 millimeters to 1.6 millimeters. So I'm hoping not to have to go more than that, but again, if I can have some mechanical analysis of this, from some mechanical experts to say, Alan, it's never going to work, or yeah, it looks good, or just do these minor tweaks. I think that would be great. So that's this side of it. Then on this side, I didn't really get a chance to. It shows a gap here, but you'll have a little water connection linking these two pieces together. And I was looking in this, again, this is just a brick at the moment, but let me just hide it. So this is with our chiplet world that I think I talked about briefly here, but I talked about a little bit more length. There's a good recording on ODSA of this, of where we place these chiplets, and which I'd recommend people watch from a better signal integrity perspective. And could we make this a substrate and get rid of the package of the big processors altogether? But one of the things with cooling this is you look at the various cooling chambers, again with the water flowing through it, and I was thinking of 3D printing that, which again is expensive, but I'm not sure how many of you heard, but there is the University of Illinois came up with an idea, and again, if you're in the military world, you'll know about conformal coating. What you do is you conformally coat the entire boarding, all of its components, with some sort of insulation material, plastic or whatever, that makes it completely waterproof. So a lot of military cards are conformally coated. And the idea that this research in the University of Illinois came up with is to conformally coat with a very thin layer of insulation, and then add a conformal coating of copper. And then that becomes, that gives you such a thin interface. They claim 700% or 7 times better thermal conduction to the fluid. So this becomes an entire, it looks like an entire piece of copper once you've finished coating it. And then you flow the fluid over this and extract the heat out that way. Without having, and it's so from a cost perspective, compared to printing a 3D a copper chamber, it will be very attractive. So let me just switch over to the website here. This is here's an article on it from in electronics design. So it was July last year. I've managed to touch base with the researcher there, and they have 2 or 3 actively funded projects that they're working on, and he would be delighted to work with us. Again, it's a university, so they'd want money. So we need to find some money to do this research. But I can put a link to this article in here. But it talks about this paraline is this insulation that they first deposit on it to insulate everything, and then they do the copper deposition. So you get this, and it's entirely connected by copper. They did do some analysis of the voltage breakdown of a number of samples. So it is still work in progress. Here's some pictures. Let me just zoom in if you can't see. So this is showing a traditional board with traditional heat sinks on and the thermal paste. And this is showing the same chips being conformally coated. And I guess this is the devices pre the conformal coating. Then there was a setup and a bunch of analysis. Anyway, you can take a read of this. But if we went with this, going back to my model, we could, the lid that I just showed we put on top, that could be something like, I don't know, carbon fiber or some plastic type of water housing that we would mount, that would physically contact the edges of the board, and somehow hopefully we could seal the lid, and it would just be a standard lid for all boards that would give you a gap between the highest components, obviously, and the lid, and the water would come in on this side from the middle. It would flow across the board and then flow out here. So that was that's the principal idea for this. Or we could still go with 3D printed copper chambers where you're landing on, where the structure, make sure you land on all the hot components, but that would be a custom design for every board. So that's one aspect.
I mean, the big advantage I see certainly as a standard is that it does allow you to standardize some of these cooling components, which then makes them, gets you some economies of scale on the manufacturing. And yeah, if this is an approach that we made to work, it massively reduces the supply chain complexity by having a few standardized components. And to be honest, you might as well go down the same route for the modules, really, for the same reasons.
Right. Yeah, so if we can normalize to these pieces that go around the module, then we could put a perimeter around the board to say, well, this is the water sealing perimeter, if that's possible. Again, then that's that would be the ideal approach. Again, so thinking about carbon embodiment, there is this need to this modularization and reuse of the same thing everywhere. So this is where this could become quite attractive. Okay, let me put the lid back on that one. So maybe this wouldn't need to be that high. This is only this thick because we were using very, very tall inductors. But looking at the trends of the NVIDIA modules, etc., and AMD, I think we can get a lot lower profile here as well, which would be good. So that's that. If everyone's okay with that, let me switch over. It might take a while to load this. I've been playing with the wall, and so there are some interesting challenges on the wall as well.
So while you load that up, Alan, it's very interesting that University of Illinois research. I'd be very curious just what powers they're looking at for that, just because I think even depending on how low that thermal resistance can be made with that, there's a reason that most of those chips now are being cooled with, you have the micro channel fin structure. I just don't know if you have enough surface area just only going directly over top of those components rather than.
Oh, interesting. Nice.
That's really where the height of that cold plate is coming from right now.
Okay, interesting. So you're saying that wicks the heat up to make more contact with the water.
Yeah, you get the increased surface area with those fins, and that's where you get higher heat transfer.
Interesting. Okay, thank you for that insight. All right, so we may be still stuck with the chamber approach, I guess. The 3D
well, I mean, you could substitute the fins for example, phase change of liquid that increases it significantly. Yeah, I don't think necessarily dead in the water with that idea, but it is a very good point that there is a reason why you still have to have some notion of heat sink in there often.
Yeah. So that's a good point. On the phase change side of things, while I was at Prague, I was learning about the different. Water needs to be treated because of the corrosiveness of it. But if you go with some of these special liquids, and you go with phase change, but then you're turning from a liquid into a gas. And apparently that means, I think Philip from Boyd said on a call a couple of weeks ago that you're turning into a gas, so you need bigger outlet pipes than you have inlet pipes. And so I don't have that in here at the moment. So
yeah, I think to pull this off, you've got to define what that liquid is fairly soon, because it is going to drive a lot of decisions.
Right.
Water is a nightmare for a whole host of reasons. It is fundamentally universal solvent.
Yeah, a chap called John Summers from RISE Institute in Sweden was actually asking a bunch of questions around this, you know, water versus the other. So he's an expert in this area, and yeah. So I mean, I became aware of it all because of Prague, OCP Prague. But yeah, this is where we need the thermal expertise. So
just quickly, the other big thing on phase change too is, I know with like 3M is discontinuing Novec, and the European Union banning those, they call them the PFAS forever chemicals.
Because they're fluorine based. Yeah.
So lots of that phase change technology, there's going to have to be a lot of research, I think, into what they can actually use for the coolant going forward.
Yeah, and actually, interestingly, John Summers was saying, I mean, I didn't realize this, it's obvious in hindsight, but water can be, by changing the pressure, water can boil at different temperatures. So you can make water into phase change, and you can treat the water for the corrosive aspects. So anyway, again, I'm no expert in this. It's just,
in terms of defining a specification, which is obviously fundamentally the point of this group, I think that's got to be a design decision you've got to take pretty early on.
No, absolutely.
It drives so much of everything else.
No, I agree. I mean, obviously, if we're going to convert to a gas, if we are going to do the boiling approach, then clearly the design's screwed already because the outlets are the same size as the inlets. So, and that's when size. Again, I've chosen the sizes I've chosen. This is all about making this as miniature as possible. Okay. So here's the wall. I don't know if you saw, I had some crude pipes before, and again, I've done this with us like a copper piping approach. I don't know if that's necessarily the way we need to do it. It might be the most cost-effective way to do it, but I've just exposed it in. So we need to look at the design of the wall. So if we just separate this out to, let me just.
Push fit poly pipe every time, by the way.
Sorry?
Push fit poly pipe is the winner every time, by the way. Copper piping is an unbelievable pain in the behind, whereas they've really got push fit poly connectors down to a fine art now.
Okay. Well, so just going through this at the moment, let me just try and start from the top down. So what we've got here is this is the wall as I would envision in the data center. These pipes actually are about 2 meters long or thereabouts, and you know, so we're roughly the height of a 19-inch rack is what the modules are consuming, and then you've got the above rack stuff that can go on. So you can see we've got 16 modules deep. And then in this example, the wall is 8 modules wide, but the wall would just keep going for the entire length of the data center is the idea. So this is just to be representative. Then up and down, every column has a cold pipe and a hot return pipe. We've got a pump here that's pumping the water around. The idea potentially, these Stolby connectors say won't leak, but you know, everyone worries about leaking. So I guess this could be a differential pressure. So if there's any air, suddenly it sucks the water away instead. I've just picked up a simple water pump and scaled it to fit here. So this doesn't represent reality here. And then there's a heat exchanger. So this would be a closed loop to just this vertical stack of 8 modules. And this is from Alpha, another company I met at Prague. They can exchange, they had a tiny exchanger, and I'm not sure if I've got the exact size of it here. I think it's actually smaller than this. They can be stacked plates together that they can easily do 15 kilowatts. He showed me a 15 kilowatt one, but said they can stack more plates and do more. Really an amazing heat exchanger for how small it is and how much power it can exchange. And then that would go out to your facilities water here. So you'd have a closed loop for each of the vertical channels for now 1.4 kilowatts times 16, you're in the 20-30 kilowatt range per stack. So that's the fundamental loop. If we just zoom down into the bottom corner, so just one of these, what I've got here is on the cold feed, I've tried to show a valve. This is like and again, this isn't representative at the moment. I've just scaled something I could find on the internet. But this would be ideally a variable, not a solenoid valve, but a variable valve where we could control the flow of water into both of the pipes. So this is 2 pipes going into the 1 module. So you can imagine the modules at the end here. I haven't shown the module. And on the return, they're just the pipes don't have any valves on them. So the idea here is that you would control the flow. If this was water-based, which again is an interesting one, they want the water temperature to be at least 65 degrees C for it to be usable in energy recovery. And so what this could do, depending on what each of the modules is burning power-wise, this could change the flow across the module so that the output temperature was always 65 C or whatever temperature you wanted. Obviously, if you went for a boiling approach, you can set the temperature that it boils off at, and I'm assuming that gives you this fixed temperature that you need. So you might not need the valves then if you went for, but then you'd need to think of this from a gas. So I've been thinking of it from staying as a liquid with all of my considerations. And again, I'm no expert. That's just the way I went with this. So this is assuming you've got 100 degrees C boiling water, and you only raise it to 65, so it stays a liquid. So that's the water side of it. And then we've got the power pins that are the 48 volts coming in to this. And this gray box. So again, the length of these pipes and the height of this gray box is probably too high. We can probably shrink this, I'm hoping, but depending on what we need for the power brick. So the power brick I had here, and again, I've crudely shown that we've got a bus bar carrying the 270 volt AC or DC or whatever the facility's high voltage is, and that would be connected. So in the power brick, it would plug into there, and then off of the cold pipe, we've got a copper feed. So this would give you some sort of conductive cooling to cool the 50 or so watts of power being burnt in this power brick. So this would be, so I'm seeing this as being a mechanical mate that you would mount the power supply onto this. And this could be bigger, you know, I just came up with this idea that this would be this part of the structure. And again, you know, structurally there's nothing in here, so somehow we'd have to work out how we build this structure. So I'm just trying to show everything we've got here. So the power would, and then 48 volts DC would come out here to feed the actual individual modules. Now, does that all make sense? And is there anything that jumps out at people as being crazy?
So
If you
my big first comment, Alan, is just to do with the fact that you're looking at those individual pumps over each column. I think economies of scale, from an economies of scale perspective, usually just thinking back to like a standard IT rack right now, it's equivalent to what you have. But for like a individual rack, if someone's deploying liquid cooling, they would have a coolant distribution unit that provides the cooling all to everything within that one rack. And then as you're looking at deployments of multiple racks, like 5 or greater, then you're looking at a more centralized row-based coolant distribution unit, and that's providing fluid in parallel to each rack of IT equipment. So I think on one hand, it's economies of scale. It probably gets quite expensive adding this many pumps. On the other hand, is the redundancy side. So
right, you get column redundancy here, right? Right.
Yeah. So what those coolant distribution units usually would have redundant pumps. So if one fails, they're still able to provide flow everywhere.
Well, I guess they're, and everything's smaller as well. That was the only thing I liked about the alpha heat exchangers. There was quite interesting at what they could do. So yeah, that's a very valid point in terms of and again, the other thing here though is this is like a permanent feature of the data center as opposed to being built into a rack that gets torn down every time. So by the way, on a redundancy front as well, Kevin Giro, I originally talked in my previous presentation about ganging multiple modules under one power supply. I'm not sure, Kevin, if when during our conversation you said, why don't you just do a power supply per module, or we could double up and do one power supply per 2 modules, and if I have one power supply, they have to feed 2 and fail over no, that's the wrong way around.
It's the other way around, yeah. But yeah,
yeah,
it's interesting. In looking at this, well, one of the things I noticed, you're trying to just use a cold plate or a plate to take the heat out of the power supply.
Another water connection in. It's only 50 watts or so for a 2 kilowatt. You said 96% efficient, didn't you?
Yeah, but you probably to get all that heat out like that is one place. It'd be interesting.
Okay, fair enough.
You have to do some analysis.
Yeah, you'd have to design around all the big power-hungry components around the back of the cold plate, right? They'd have to be mounted. I remember old amplifiers in the 80s where all the components were actually, screwed to a big cold plate, a big heat sink.
Yeah, and it's sort of that way, but you'd have to put them all on one side. And
right.
Having water going through the power supply would be a lot easier on the power supply guys.
Okay, so yeah, I guess that was another mating point for water, which
right?
Was I guess my only concern there, but I guess it's a possibility.
Okay, I got some other ideas too. Go ahead.
Two thoughts that I came up with looking at this, Alan, is if you can get rid of the valves, do, because having worked in oil and gas at one time, amongst other things, the one thing that always is trouble are valves. So the less valves you have, the better. And secondly, that reminds me of an old school telco racking. So in telecom exchanges, you tend to have racks that look a bit like that, and maybe that's the answer for finding a structure solution. There are folks like Crone out there who build racking to house electrical components like that for telephone exchanges. Just a thought.
Okay, interesting point on the valve. Go on, somebody else.
I was going to take on to what Greg said there about the valves. Another reason, another benefit, Alan, of having a more centralized coolant distribution unit with the heat exchanger and pumps is that they actually can have like a temperature control mode where you're controlling overall from a bulk perspective the output temperature, so keeping it at that 65 degrees, because it just monitors the coolant temperature going out, and then it can adjust the amount of facility flow that's bypassing or not, and keep that temperature consistent.
So that's a good point, but where my head couldn't get things straight on that is that if I've got a big GPU here that's buffed in its ass and burning a kilowatt, and everybody else is only burning a few hundred watts, or say for sake of argument, then I change the flow of the entire, and I can't change what I end up doing is I push this one over its heat limits while everyone else are really chilled. Does that make sense? Whereas I guess a gas approach means that everything boils, so you would automatically get more flow.
Yeah, that is the beauty, is they tend to be quite self-regulating systems.
The gas ones.
Yeah, we got phase change. Yeah.
Right.
Yeah, but in general, on single phase, Alan, you're right. you are designing the system to the worst case scenario, and so yeah, when it'd be running them all, assuming that you're trying to cool it in its worst state. So that's where the valves can be beneficial to have more targeted cooling, but yeah,
Is there
you generally work on worst case scenario. That's it. You design around that.
Well,
You can't get too cold.
but this is the problem, you see, so one of the fundamental things we're trying to cover here is that we need energy reuse, and that means we need the temperature of the water to come back to us at a good high temperature. And the problem is if half of the data center, if it's all off of one big feed and half of the data center is idle while the other half is maxed out, by definition, you're going to have to keep the flow through the one that's maxed out, which will easily give you 65 degrees C, but everything else will be giving you the same temperature as going in, coming out, for sake of argument. And therefore that'll mix to 30 degrees C. So you're going to need the ones that are working their asses off to go up to 120 degrees C. And therefore you're not going to be able to do energy recovery. Whereas with valves here, or with phase change, I guess, so I'm wondering, is there work can be done to make a valve more reliable? But
you can aggregate it upstream is the other option.
no, you can't, because I get the same problem. I did think about putting a valve just at the top, but you then get the same issue in the column of modules with one module.
They're saying you can aggregate the energy further up through the heat exchangers in order to get you up to your 65. I mean, there are other ways of doing the valves. I mean, I can put you in touch with a guy who's an expert in memory metals, and he's done some interesting things with valves that are just made from memory metals, and then there's no mechanical moving parts and therefore highly reliable. But it all starts getting quite exotic quite quickly.
Okay, I realize we're already almost at the top of the hour. I guess my call to action is a request for, is there any chance that maybe I can throw the 3D models to some of you experts and you can maybe get a little bit of resource to just tell me how mad I am, and just to sort of see how, whether we're on to something here or we need to go back to ground zero, and if we go back to ground zero, what is it we're needing to change?
I was looking at it and thinking it's a bit 2D, and I was wondering if you could consider doing things like drawers of compute.
So the drawers then become unserviceable. That's what part of this could all be serviced by a gantry robot as well, sort of thing.
If you do something as a drawer that you can pull the whole drawer out, but the thing is, if you do something as a drawer where you can actually have a pool of fluid at the bottom, which things are sitting in, it may be easier to do some of the cooling.
Right, the pool of fluid. Yeah.
So you could do something where you're putting your boards in a way where the one end is sitting in fluid that cools it.
Right. Yeah, I understand what you mean by the 3D, but the only thing I would say on the 3D, although you could have, these walls could be a lot closer together, so you'd have a ton of walls. Anyway, we've gone over the.
Yeah, I mean, there's quite a lot of clearance on that if you're actually trying to move things in and out. So the question is it efficient use of space?
Yeah, so it would be a gantry robot that would be servicing this. It would, in an ideal world, ultimately.
Mm-hmm.
But you could also, I was thinking as well, you could make this a double-sided wall as well, so the wall could service both sides as well.
Yeah.
That would be the other aspect. Okay, all right. Well, enough for one day. Well, if anybody can help out, then please let me know. Okay, Callum said he can talk to his engineering team, so that's great. Thanks, guys. Much appreciated.